Our home planet, Earth, is one of 8 planets of our solar system. Every planet in our solar system orbits a star we call the Sun. Our Sun is one of about 100 billion stars present within our own Milky Way galaxy. Our galaxy is one of, it's estimated, up to about 200 billion galaxies present within the observable universe alone. The cosmos is a very vast place indeed, the observable universe spanning approximately 26 billion light years across. And yet, at one time, this vast universe was nothing more than a point, with a diameter of about a billionth of 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 a meter across. That's pretty small. How did something so small give rise to what we see today? The image currently on your screen is a summary of the events that led up to the universe we live in today. The rest of this video podcast is going to be covering each of the stages in the history of our universe until we end up where we are today. It'll be best to start off right at the beginning. Well, not at the very beginning. Why not? Quite frankly, we just don't know what happened then. Gravity requires a quantum explanation because the compactedness of space-time is not something our current theories can handle. Developments in quantum gravity will give us a fuller picture of the universe during the earliest time in our universe. Right now, our best quantum gravitational theories do tell us what might happen during this era and even prior to it, if that makes sense. But it's just too early to tell what is correct and what is not. So, quite frankly, we do not know what happened during this very early period in our universe. After this first bit of time, we step onto some solid ground, the Grand Unification Epoch. This brief moment in the history of our universe takes place when every other fundamental force of the universe, besides gravity, is united into one grand unified force, hence the name. The reason they are unified is because, as the temperature rises, the forces begin to behave in the same way, until, during this era of time, they are indistinguishable from one another at this temperature level. We also have a quantum mechanical explanation of describing these other forces. We do not have a quantum mechanical explanation for gravity yet, which is why the first epoch is unknown. Things are really only stable here briefly. The universe is teetering on the edge of doing something really, really big, and one of the fundamental forces will cause this something to happen. Okay, I was just kidding. I added that sound to get a point across. The Big Bang was not, I repeat, was not an explosion. It was an expansion of space-time. I know a lot of authors who try to popularize the Big Bang call it an explosion, but it really is not a correct thing to say the Big Bang was an explosion. It was the expansion of space-time. And during this era, the expansion was very, very rapid. It is known today as inflation. When a strong nuclear force separated from the electroweak force, and that's just electromagnetism coupled with the weak nuclear force, it gave rise to and set off a field in the universe known as the inflaton. The inflaton field was originally sitting at some positive energy value upon its conception. The separation of the strong nuclear force set the inflaton field cascading towards a lower, more stable vacuum state, in which it releases its energy as it goes along. The way it releases its energy is by expanding, and expand it did. The universe went from being several times smaller than a proton to being about the size of a melon, or even greater, within the tiniest fraction of a second. That's a lot of energy to be stored up. And yet, we've never observed this inflaton field. What makes us so sure that it even existed, or did what it did? The answer is that inflation, like any scientific theory, makes predictions, and these predictions have been verified by observation. For instance, inflation predicts certain peaks in the cosmic background radiation, something we'll discuss a little later. And when we observe the background radiation, we find exactly these peaks. Mind you, inflation is not just one theory, it's a bunch of them. And that image I'm using is just one model of inflation. But the notion of an inflationary epoch is well backed by the evidence, regardless of what specific model we look at. The devil is in the details of each inflationary theory, but the idea overall is correct. Once the universe stops inflating, the rest of the energy of the inflaton goes into forming a lot of particles and radiation, equals mc squared, right? At this point, we can imagine the universe being enveloped in a thick fog of elementary particles and light. We now enter a new period in the history of our universe, the electroweak epoch. Keep in mind, the universe has still not existed even for a full second yet. A lot has happened in the first few moments of time. In the electroweak epoch, there were three separate fundamental forces: gravity, the strong nuclear force, and the electroweak force, which, as I said before, is just electromagnetism and the weak nuclear force coupled together. The reason being that at the current temperature, the two forces effectively act as one. During this era, the temperature is hot enough to provide energy to the particles within the universe that lead to the creation of particles we don't normally see. For instance, the W boson, which is the carrier of the weak nuclear force, is the particle that mediates the force. As the universe continues to expand, it cools, and the dropping temperature allows for one last force separation, giving us the four fundamental forces we know today. Alright, so the four fundamental forces are all separate now. Now what we need are some basic building blocks of atoms. I'm not talking about protons and neutrons yet. Protons and neutrons are built up of even smaller particles called quarks. Earlier in this new epoch that we are going into right now, the quarks have too much energy to be bound together, and so they sort of drift along by themselves, something we never see today because the temperature is just not hot enough to allow them to drift around by themselves. However, as the universe continues to cool, they bind together to form what particles are known as hadrons. Some examples of hadrons are protons and neutrons. They differ from a group of particles known as leptons. The difference is, hadrons feel the strong nuclear force and leptons don't, which means leptons don't really bind together to form new particles. An electron is an example of a lepton. While a proton is composed of a few quarks glued together by the strong nuclear force, because that's what the strong nuclear force does, it binds together atomic nuclei, and these objects that are hadrons, these protons, they bind the quarks together to make these protons and neutrons. The electron is just, well, the electron. It doesn't combine to form anything because it doesn't experience the strong nuclear force. It doesn't feel that gluing force to make it combine with other leptons. Now, one problem I should mention is that we don't really know exactly why there's more matter than antimatter, more quarks than antiquarks, or more electrons than positrons. It's another field of current research. It's known as baryogenesis. Suffice to say, at the end of this era, we had a whole bunch of protons, neutrons, and electrons, along with a bunch of other particles, just flying around in the universe, having too much energy to do anything besides, well, fly around. It would take a little more cooling for them to form atomic nuclei, which is our next topic. Alright, so the temperature got cooler still, and now the floating protons, neutrons, and electrons began to form atomic nuclei. A lot of extra photons were also drifting around during this time. Photons are just light particles, by the way. However, the photons were just bouncing around in circles because the high-energy electrons that were around there at that time, which were helping to make the basic elements like hydrogen and helium, wouldn't let them pass through. The universe at this time still looked a lot like a thick fog. As time went on, the universe experienced what is called Big Bang nucleosynthesis. This is the production of the lightest elements, hydrogen and helium. The basic forms of hydrogen and helium were produced, and hydrogen was about 10 times more prominent than helium. The amount of hydrogen and helium was a prediction made by the Big Bang theory that turned out to be wholly accurate. Once everything got settled, the electrons had lost some energy in combining with the other particles to form the basic elements, and the photons were kind of free to travel on their way, move throughout this cloud of electrons. And they've been doing so ever since. In fact, the Big Bang theory predicts we should see this original light, though it's cooled since then to just a few degrees above zero, so the wavelength has changed, and we expect it to be in the microwave part of the electromagnetic spectrum. Light being just a part of that. So here it is, the cosmic background radiation. This is the newest imaging of it from the results of the WMAP project in 2003. There was an earlier project in 92 about, that's when we got the results from the COBE project, which is the initial one that took a look at the cosmic background radiation. What you see now is a light from about 380,000 years after the Big Bang that's been traveling to us ever since it got free. The fact that this existed at the predicted wavelength is perhaps the strongest piece of evidence for the Big Bang theory that we have today. No other theory can account for this cosmic background radiation. We've now left the early period of the universe and have moved on. We now have all the basic building blocks of stars and galaxies. All that we need now to happen is, well, for them to form.